What's up, Sim Scientists? It's your boy, Sim Science, still alive, still kicking. As some of you may have heard, I had a bit of an incident, incident in first period the other day, which was funny as you heard me laugh until it turned into this whole big mess with a bunch of issues and a bunch of doctor's appointments and some strange stuff going on. Weird that these type this stuff is weird for someone as young and vibrant and handsome as me. So we're looking into it. We're getting it figured out. Unfortunately, it's causing a lot of stuff I have to try and handle. So I am not able to be with you guys today, Friday, where if you're watching this there, but I'm not there. Friday, you look up, there's a sub, look at him or her. It's not me. It'll never be me. They can try as hard as they want. They're not going to be me. But anyway, whatever's going on, my Sim Scientists come first. Although I will say it's a little odd. I've been monitoring Twitter and Instagram pretty closely, and I haven't seen like hashtag prayers for Simpson or hashtag prayers for Sim Science. I haven't seen any of that stuff trending, so it's a little bit odd. I kind of expected more of an international rise of coming together and whatever. Maybe I'm just being a little over the top and a little bit egotistical, but anyway, I'm trying to get it figured out, guys. I should be back Monday no matter what. I think probably just going to start ignoring doctors at this point because they're keeping me away from my love, my passion, which is obviously chemistry and my Simpsonites. So anyway, I'm going to do as much as I can right now, live, in class, live Sim Science video, except it's not live, to get you guys, make sure we're all on the same page. I'm planning on doing a test Tuesday, so hopefully Monday we can review. I'll have a study guide for you guys, and we can move on to a test on Tuesday, as long as I can stay conscious for the majority of the class at least. So looking back on page 132, second question, we didn't finish it in a couple classes. You were supposed to finish it on Thursday. You should have gotten negative 890.25 kilojoules per mole, which is because negative exothermic. That's what you should have gotten. If you didn't get that, we got issues. If you didn't get it, look back at the previous problem in the example and try to get to the point where you're doing your calculations correctly to get to this answer right here. If you're very confused on that stuff, we will have time to look at it again soon enough. Okay, let's see. Some of the stuff got mixed up as I was putting it back in. So yes, Thursday, should have done some of this. So let's look at what we're moving on to now. The next thing is talking about exothermic and endothermic reactions in terms of energy. So in what we were just doing with enthalpy, we were seeing how the breaking of bonds in the reactants is going to require energy, and then the forming of bonds in the products is going to give off energy, and it's like an investment of energy in, and then how much energy you get out. Think of it like money. So now we're going to start talking about how that energy translates to thermal energy, heat being released or absorbed by that reaction. So if heat's released, it's exothermic, which means that the energy given off by forming the products is greater than the energy required to break the reactants. So you're making more energy than you put in. You're making more money than you put in. You have a net gain, a net release, a net excess of energy. So when that happens, you feel heat around the chemical reaction. The beaker's going to get hot. There might be fire. You're going to feel heat in a reaction that's exothermic, an exothermic reaction that's releasing thermal energy. On the other hand, an endothermic reaction is going to be when the energy required to break the bonds is greater than the energy released when you formed the bonds of the products. So what it takes to break the reactants, the energy you put in is more than the energy released. Okay, so you're investing a certain amount of money, but you're not making more than that back. It's a net loss. A net amount of energy is being absorbed by the system. So an endothermic reaction, you're having an absorption of thermal energy. okay? So when we do that in a chemical reaction and the reaction itself is absorbing energy, it's going to be cold. The beaker is going to feel cold. The solution is going to get colder. It's going to give off, not give off, but it's going to absorb heat, leaving its surroundings colder. Okay, it's kind of tough to think about because, again, like, it's easy for exothermic because that's giving off heat. That's easy to conceptualize and see. An endothermic reaction is sucking in that heat, therefore leaving the surroundings, which might be the beaker or the air around it, colder. It's a little bit different than physical changes like freezing, melting, boiling. When we talk about those as endothermic, exothermic, this is a little bit different because now we're talking about chemical reactions and their exothermic or endothermic natures. Okay, so we'll come to this question in a second. This is what you should have put in this little mini lab experiment. You probably saw I have set up in the back. Little did I know what would transpire the following morning, but that should still be set up, and we should be able to do that when I get back. Hopefully, I think it's important enough. We'll see. Anyway, okay, so let's look at this. I asked you to highlight this yesterday. Hopefully you did. So we have two types of reactions here. We have exothermic reactions and endothermic reactions, chemical reactions. Okay, so as I said, an exothermic reaction occurs when the energy used to break the bonds in the reactants, so we're breaking the bonds in the reactants, which requires energy, like the two basketballs rolling to the bottom of a hill. It's going to take energy put in to push these back to where they started. So breaking bonds requires energy. Energy is used to break bonds. So that energy is less than the energy released when new bonds are made in the products. The energy released when new bonds are made in the products. So an exothermic reaction occurs when you have more energy being released than you put in. Okay, and that extra energy is given off as heat. There's a temperature rise around the surroundings of the reaction. So an exothermic reaction is associated with a temperature rise. Combustion is a good example of an exothermic reaction because you can feel the heat given off if you get close. So something burning, we feel heat because that's giving off more energy than it takes to start it. The reactants have more energy than the end products. It also indicates that the enthalpy change is negative as heat is lost to the surroundings, resulting in a temperature increase. Okay, so the enthalpy change is negative. We saw that in our enthalpy calculations. It's negative because you're giving off heat. You're losing heat. You're losing heat energy to the surroundings, increasing the temperature of those surroundings. Okay. Endothermic reactions. So an endothermic reaction is going to occur when the energy used to break the bonds in the reactants is greater than the energy given out when the bonds are formed in the products. So again, we need energy put in to break the bonds, and then energy is given off when we form bonds. So breaking the bonds in the products, or breaking the bonds of the reactants, that's going to require more energy than the energy we get given out when we form the bonds of the products. So you're putting in more energy than you're getting out. So the overall reaction takes in energy, and the temperature is going to decrease. Temperature decrease in the surroundings. Electrolysis is an example of an endothermic reaction. We talked about electrolysis a little bit as a side thing earlier this year. Probably don't remember. And then the endothermic chart is what we're about to talk about. Shows that your reactants start off with less energy than the end products absorb. Hold on, back. The reactants start off with less energy this time, and the end products have absorbed energy. So your end products have more energy than the reactants you started with, because overall the system absorbed energy. The enthalpy change of the reaction is positive because the energy is taken in from the surroundings, temperature decrease, resulting in temperature decrease. So you're having energy taken in. That means that you're going to have a positive change in enthalpy because energy is getting taken in. Overall, when you have the reaction, you're putting in more energy to break the bonds than is given off when you form the products. So that means that the total energy you end with is greater than the energy you started with, because overall in this reaction energy was put in. That's what it meant up here when it said the reactants have more energy than the end products, because overall you're losing energy. So the total energy of the products is going to end up being less than what you started with. Okay, so that's what we're getting at here. The key things are exothermic reactions give off heat, endothermic reactions take in heat and therefore feel cold in the surroundings. That's how the heat is moving within these things. With exothermic reactions, you're giving off more energy than you're taking in. And with endothermic reactions, you're taking in more energy than you're giving off. Okay, so the last thing we're talking about in this section is potential energy diagrams for endothermic and exothermic reactions. This get cut off a little bit, probably should say reactions. So yeah, we're going to talk about potential energy diagrams for endothermic and exothermic reactions. So this shows us basically the energy you start with your reactants and the energy you end with your products. So what we were just talking about at the end of both of these little mini readings about the energy change, the total energy in the system. So these handouts are in the paper dispenser box thing. If you're listening to this and nobody's handed them out first, maybe hop up and pop these things around. You're going to cut them out. Oh, I should have printed it out so that they were together like this. I did not do that. So you're going to have to cut out two separate. Oh, that would have been so much smarter. Oh, well, it's your guys doing work, not me. So you're going to have exothermic and endothermic, highlight the two. So you know, because they're very, very similar words, you want to make sure you're keeping track of what you're looking at. Okay, so get that done, pause the video, get that done, and then get back in here. So first, let's look at an endothermic potential energy diagram. So this, whoa. An exothermic potential energy diagram. So an exothermic reaction, let's take a step back and think about what it is. So we know that in an exothermic reaction, exo, exit, out of, we are giving off energy. In this reaction, we're going to be giving off energy. That means that the energy it takes to break the reactants is less than the energy that's released when we form the products. So overall, there's more energy within the reactants than there is in the products. And that's what we see here in this line. Okay, so here, got a lot of colors. I kind of want two similar ones, or should I go opposite? Yeah. Here we have the reactants. And here we have the products. So, what happened? Well, this is where we start. So let's look at our axes first. First, we have potential energy here, the energy contained within this system, these reactants, these products at any point. Down here we have the reaction pathway, which basically you could say is time as it goes this way, as the reaction happens. So we're starting here with our reactants. This is the potential energy contained with our reactants. There's no numerical values on this y-axis, but this is where we're starting with our reactants. So this reaction starts to occur, and then it takes some amount of energy to start it. That's our activation energy. I think we've touched on this before. You might have heard the term before, but any reaction, it's going to take something to start it. Okay, even, it can be very small for spontaneous reactions that happen easily, but something has to happen to start it. So it takes some amount of energy to start it. That's the energy that's going to be taken to break the bonds of our reactants. So if our reactants are A, B, and C, D, this energy here, this activation energy, is what has to go in here to break these up. So some amount of energy is getting put in. This right here, this activation energy, is our energy being put in to break these things up. So we put that energy in, and then the reaction proceeds. And you see this line comes down, 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 all the way to here, to our products. So here is the potential energy of our products. And here, the difference between these two things, between the energy of our reactants and the energy of our products, that's our change in enthalpy. That's the change in energy. So what happened? What had more energy, the reactants or the products? Hopefully you said the reactants. So down here, if this is a double replacement reaction, we have AD plus BC, or I should say CB. Okay, so this energy here, this amount of energy, is what was released when we formed these things in an exothermic reaction. Okay, and obviously the energy that was released is greater than the energy it took to start this. So this energy that it took to break these things, the total energy of formation of the reactants was less than the total energy here, the energy it took to form these things, aka the heat of formation of the products. And this gives us our total change in energy. So for an exothermic reaction that proceeds like this, there's an overall loss of energy in the reaction. And that's going to be released as heat. That's what we see happening here. That's why the reactants have more potential energy than the products, because overall this reaction has lost energy, has given it away to the surroundings. Okay, so now we come to our endothermic potential energy diagram. So you can see there is a flip here. This is the potential energy of the reactants to start with. And then up here, around here, is the potential energy of our products. So what's different about this versus an endothermic reaction, or the difference between this and an exothermic reaction? Well, look at this. This is our activation energy here. Here, activation energy was really small. Here, it's really big. Okay, because in an endothermic reaction, the energy that's taken to break these, the energy that has to get put in to break the bonds of the reactants, is going to be a lot more than the energy it takes. The energy it takes to form the products. Okay, so our total change in energy is going to be positive. There's energy gained. The potential energy of the reactants here is less than the potential energy of the products. The products have more energy than the reactants did, because all this energy had to get put into this for this to happen. And it still comes down a little bit, but overall, it's a big increase in energy of this reaction. Because here, the activation energy, the energy required to break these bonds, is really big. And then here, we have this little dip, which is the energy released when you form these bonds. Overall, the energy is put into this system. The products have more potential energy than the reactants do. Energy of the system increased, and this is going to suck energy out of the surroundings, making it feel colder. Okay, so now I'm going to show you some more charts. If I was in class, we do this on a whiteboard. I just want you to be able to tell me if they are endothermic or exothermic, and I can hear you, so say the right answer. For this one, is this an endothermic or exothermic reaction? Hopefully you said it's endothermic, because here we have our reactants, here we have our products. Overall increase in energy of the system, large activation energy. This is your activation energy here. Large activation energy, smaller energy, heat of formation for the products. This is the amount of energy given off when you form the products. Overall increase in energy for the system, endothermic. What about this one, endothermic or exothermic? Hopefully, again, you said endothermic. Here's where we start with our product reactants. Here's where we end with our products. Overall, an increase in energy of the system. Okay, we have this for activation energy, and then we have this for the energy given off when you form the products. Endothermic reaction overall, gain of energy. And what about this one? Hopefully you said exothermic pretty quickly. Here's our potential energy of our reactants. Here's our potential energy of our products. Overall, a release of energy, a loss of energy, smaller activation energy, and larger heat of formation of the products, larger amount of energy given off when the products are formed. Okay, so this is a exothermic reaction. And one more. Endothermic, that's right, good job. So again, the total energy of the system is going up. Total energy in this reaction is going up. Large activation energy put in, a lot of energy put in, and just a little bit given off. So overall, we're gaining energy in this reaction. Okay, this is what you're doing at the bottom of page 134, underneath this stuff. Okay, you're going to draw an energy diagram on graph paper. So I hope there's graph paper over there still. Go check that out. And again, if you found it, you can pass it out and then cut it out so that you don't need that much. So make your potential energy graph, number the axes so that you're able to graph something, draw an energy diagram that has a potential energy of the reactants at 350 kilojoules, activation energy of 100 kilojoules, and a potential energy of the end products of 250 kilojoules. Then I want you to tell me if it's endo or exothermic, and I want you to support that decision with what you see going on. And you could go even further with this, and you could label the activation energy, you could label the total change in enthalpy, things like that, like we just discussed. That'll help you really solidify your understanding of what's going on. But definitely give me evidence, give me a few sentences at least to support this decision on whether it's endothermic or exothermic. And it might seem obvious just from the pattern that we've seen, but I want you to actually tell me what you're seeing that's making it endothermic or exothermic. Okay, and that's it. I don't know how long this video is. I don't know if it's taking up enough of your time in class. Yeah, but maybe to increase the time in class, I'll try. I might be bored tomorrow. I'd like to just be bored at some points, depending on where I am. But if I'm sitting waiting or doing stuff, whatever, I'll be trying to monitor the comments as much as I can. So if you're wrapping this up, feel free to shoot me a question in the comments about anything that is appropriate. I will delete any comments that are rude or inappropriate. But if you want to ask me a question, or if you have a question about this video, obviously a question about the content comes first. But questions, I will be happy to answer them as best I can. Again, I hope to see you guys very soon, have this all sorted out, and be back with you guys as soon as I can. That will certainly be ideal for me, as I'm sure it is for you.